When the saga of interstellar visitors reached a new high point, scientists were presented not just with a solitary object, but with what appeared to be massive unknown objects associated with the interstellar visitor labeled 3I Atlas. This event stretches our imagination, calls into question our understanding of cosmic wanderers, and forces a reconsideration of the kinds of bodies that can traverse the galaxy and enter our solar system. The baseline facts: 3I Atlas, formally designated as the third confirmed interstellar object after 1I Oumuamua in 2017 and 2I Borisov in 2019, was detected moving at high velocity on a hyperbolic trajectory, not gravitationally bound to our Sun's domain. As telescope networks such as the Asteroid Terrestrial Impact Last Alert System, ATLAS in Chile, and other global observatories honed in on this visitor, some novel features emerged, features that do not neatly map to our conventional understanding of comets or asteroids. Among these, the detection of what are being described as massive unknown objects associated with 3I Atlas has rattled the astronomical community. While the exact meaning of unknown objects may vary, the usage here refers to large-scale anomalous features, potentially fragments, satellites, or companion masses that defy easy categorization. In the weeks surrounding the discovery, the unusual behavior of 3I Atlas began prompting more radical lines of inquiry. Its size appears above the typical dimension of solar system comets. Estimates suggest a nucleus up to 5.6 to 6 kilometers in diameter. The hyperbolic orbit indicates a celestial body coming in from interstellar space, traveling far too fast to be captured by the Sun's gravity. Yet more puzzling was the apparent presence of auxiliary components, massive pieces or objects seemingly moving in conjunction with the main body or shedding from it. Though details remain preliminary, the implications are vast. At the heart of this revelation lies the question: what exactly are these massive unknown objects? Several possibilities present themselves, each with divergent implications for our understanding of the cosmos. One scenario envisions the main body as shedding one or more large fragments, giant chunks of rock, ice, or mixed material that break away and continue in similar trajectories. In this conception, the unseen objects are detached remains from 3I Atlas, liberated by tidal stresses or thermal fracturing as it approached the Sun, or even collisions with micrometeoroids. If true, this suggests that the body already underwent significant internal stress before arrival, hinting at how interstellar objects may evolve over billions of years. Another possibility posits that 3I Atlas is part of a binary or multiple object system where the massive unknown objects are co-travelers, perhaps small companion bodies orbiting the main nucleus, akin to moons or satellites. Such systems, while common for solar system asteroids and comets, have not been clearly recorded for interstellar visitors. If verified, this would be the first time we observe an interstellar object with companions, hinting at more complex origins in its home system and a richer dynamical history. A still more provocative possibility is that the objects are encased structures or non-natural accumulations, perhaps large aggregated masses bound to 3I Atlas, possibly even active constructs, though this lies at the speculative fringe. In some interpretations, the unusual features of 3I Atlas, including atypical composition, emission profiles, and structure, have been taken to hint at something beyond a standard icy comet. For instance, traces of material outgassing or emissions not typical of solar system comets have been recorded. What unifies all these possibilities is the recognition that these massive unknown objects open a window to phenomena rarely, if ever, seen: large interstellar composites, active fragmentation processes en route to the Sun, or even companions to an interstellar body. That such an object entered our neighborhood is inherently exciting, and that it may carry additional large masses amplifies the implications. The detection of these massive unknown objects associated with 3I Atlas underscores the fact that our solar system is not as isolated as once imagined. That an interstellar visitor arrives and carries structural or compositional complexity suggests that the galaxy is littered with such wanderers, many of which may go undetected until they cross observational thresholds. For planetary science, this implies a new class of targets: interstellar bodies with internal structure or companion masses. Traditional models of comets and asteroids revolve around bodies formed within our solar system, often undergoing well-studied processes such as accretion, gravitational perturbation, and evolution by solar radiation. When a visitor from another star system arrives, it may bear hallmarks of entirely different environments and perhaps wider structural complexity. The presence of massive unknown objects suggests past interactions, collisions, or formation in a multibody environment before ejection. These bodies could have been part of a planetary system's debris disk, a binary planet-moon system, or even remain bound as clusters long after ejection. From the perspective of astrobiology and planetary formation, such a discovery expands our understanding of how material cycles between star systems. If 3I Atlas indeed carries large secondary objects, then ejection of multi-body systems from planetary systems might be more common than assumed. Such ejected systems may preserve, frozen in time, information about their origin, from chemical composition to physical structure, and offer rare glimpses into foreign planetary systems. Furthermore, for planetary defense, the event is a cautionary lesson. Though the trajectory of 3I Atlas poses no threat to Earth, its closest approach remains safely distant. That said, the arrival of a large interstellar body, accompanied by massive objects, highlights the diversity of potential threats and the need to broaden surveying efforts beyond the familiar catalogue of solar system origin bodies. Objects approaching from outside the solar system do not necessarily follow the same dynamical rules or have the compositional signatures we associate with known comets and asteroids. Their behavior could be unpredictable, fragmentation could occur en route, and companion bodies could diverge. On a philosophical level, these massive, unknown objects broaden our existential vision. They serve as reminders that the Milky Way is a dynamic ecosystem in which objects wander between star systems. We tend to think of our solar system as a self-contained arena, but in truth the boundaries are porous. The presence of large companion masses in an interstellar visitor suggests that planetary systems may lose not just single bodies, but entire fragments or groups of bodies to the vastness of space. When one of those comes by, it gives us an opportunity, a fleeting chance to interrogate foreign environments without ever leaving our solar shores. Since the identification of 3I Atlas, the astronomical community has mobilized quickly. Observatories across the globe have pointed their instruments toward the visitor, capturing imagery and spectrographic data. High-resolution telescopes, such as the Hubble Space Telescope, have refined the size estimates and revealed a coma of material around the nucleus. At the same time, space-based assets such as the James Webb Space Telescope have begun probing its infrared signature to understand its volatile content. Now, the additional twist of the massive unknown objects associated with 3I Atlas complicates the observational strategy. Astronomers must attempt to distinguish primary nuclear signatures from secondary objects, a challenging feat given the vast distances and faintness of the target. The relative brightness of companion masses, their trajectories relative to the main body, and their interaction with the coma and dust trail all become variables to resolve. Sophisticated image analysis, potentially adaptive optics corrections, and long-term tracking will be necessary to map relative motion and confirm whether the unknown objects are bound companions, shedding fragments, or simply coincident background objects. In parallel, modeling efforts will attempt to reconstruct the origin of 3I Atlas and its companions, simulations of ejection from a parent star system, the effects of gravitational perturbations, and expected fragmentation during long interstellar travel will help contextualize the massive unknown objects. If these objects are indeed companion bodies, then the parent system of 3I Atlas may have been a more complex multi-body system, perhaps with planet-moon dynamics, binary minor bodies, or a fragmented debris belt. The sheer size of the unknown objects will force reconsideration of formation models. Could a multi-object system be ejected intact? If so, how common might that be in our galaxy? Additionally, coordination among space agencies has ramped up because 3I Atlas will pass relatively close to Mars's orbit in late October, about 1.4 astronomical units from the Sun, before heading toward the outer solar system. Observatories and spacecraft around Mars and beyond are being urged to capture as many observations as possible. If the companion masses separate further or produce distinct trails, instruments aboard Mars orbiters or even Earth-orbiting telescopes may capture data that ground-based systems cannot. The timing is tight. The window of optimal orientation and brightness is limited. Hence, scientists are racing to capitalize on this fleeting opportunity.